Hi everyone, I'm Shen Wang from New York University. Today I will present our work on public transport planning. First, let me tell you a real story. New York City is redesigning bus networks in its 5 boroughs. For example, MTA, the Metropolitan Transportation Authority, is animates 400 stops and add new routes in the Bronx. However, according to the website of MTA, this task is complex as several features need to be considered to make the public resource allocated fairly. Specifically, MTA website lists several features that need to make trade-off. Riderships are always the most important features, but besides serving most riders from dense area to suburban area, the bus network should also have wide coverage in other areas. Stronger connections will give more transfer options to passengers and will serve more people than one seat rides. Other features includes whether designing more stops or not. Overall, in this work, we focus on meeting the demand of riders and aims to increase the connectivity of bus network as New York City has enough stops and there is no need to build new. Existing work on bus route planning are driven by trajectory data, which can be accessed in multiple ways, such as New York City and Chicago taxi trips. For example, 3 years ago, we proposed to design a new route to attract the most passengers between two stops. But in that work, we just consider the ridership and ignore the connection. To our best knowledge, there has not been any study that can plan a route to optimize the connectivity of public transport network yet. And we propose a new problem called city bus, which will take care of both. Here is the outline of the following presentation, which includes the definition of city bus, challenges, our problem designs, and experiments. If we consider these two features, the connectivity and the demand, we mainly have three kinds of data: the road network, the transit network, and the trajectory. The road network and the transit network can be both modeled as direct undirected graphs, and the trajectory can be pre-processed and mapped to the road network as shown in the figure. The dashed line shows that a new edge is necessary for transfer between the two blue bus routes. We choose lateral connectivity, which is arguably the most proper one for transit network, since it will not show drastic changes by small graph alteration or no change by big graph alteration. Instead, it can monetarily evolve with more modifications. To verify this in real transit network, we randomly remove existing routes from Chicago and the New York City transit network gradually, and we observed a nearly near decrease of lateral connectivity. We choose to extend an edge-based trajectory simulated measure, which is state-of-the-art of network constrained trajectories. With this measure, we define the commuting demand for bus route as the sum of all intersected edges lengths. Hence, we can avoid scanning every trajectory and accelerate with pre-computation on how many trajectories crossing each edge, which is defined as the frequency. Then we adopt a linear combination to weight these two objectives, where a configurable parameter weight can measure various planning requirements. Optimizing the objective of city bus is challenging because it is a combination of two complex constraint optimization problems over graph. And optimizing demand only by setting weight as 1 is a TSP problem, which is NP hard and has no approximate ratio. A straightforward solution is to generate a large number of candidate paths from the graph and choose the one with the highest object value. Then, for every candidate, we need to compute the connectivity of the enhanced network. Unfortunately, it is computationally expensive to evaluate the objective function of city bus, as the calculation of connectivity requires the eigenvalues of the adjacency matrix. Next, I will tell you how our city bus planning a bus route efficiently. We employ expansion-based graph traversal merger to solve city bus. We first select edges with high demand in the graph for expansion in the initialization stage. In the expansion stage, we scan candidate path by initializing candidate seeds with all, and then incrementally add label edges as new candidates. In the verification phase, we compute the connectivity of each candidate and update the results if the candidate has a higher object value. The above two phases will be conducted iteratively until meeting the terminational criteria. The number of iterations exceeds the predefined threshold, or there is no more candidate in the queue. As we can see in the connectivity estimation, is conducted in every iteration. Its efficiency is critical in this algorithm. Here, our main contributions are the faster approximate estimation algorithm with guarantees and a much faster estimation with pre-computation. We can efficiently calculate the lateral connectivity of a transit network by estimating the adjacency matrix trace. Written the proof that its approximation error can be bounded within 101%. Then we derive two upper bounds on the connectivity of a new network enhanced with a group path. Due to time limits, we will not animate all the details, but the one thing need to mention is that our algorithm can achieve up to 1,000 times speed up. Although employing the length source method can boost the efficiency of estimating connectivity and the upper bounds, a single iteration's running time is still non-negligible, as shown in the last slides. Hence, within 1,000 of iterations, it's slow to terminate this algorithm. In the figure, we show that reducing the connectivity to a linear aggregation function for fast updates with new edges is very precise. Then pre-computation is conducted on each edge's demand and connectivity, which can accelerate the algorithm dramatically by using a greedy strategy. Next, let me tell you how we evaluate our proposed algorithm. You can also download our code and the data from GitHub. We focus on two cities that have public taxi trips, and their network data can be easily accessed online. Since taxi trips only contains 2 points, we converted them to trajectories using the shortest path between two ends in the road network, and the table shows an overview of our dataset. We mainly test the running time and the convergency of our algorithms. Since CityBus is proposed for the first time, we will mainly compare our proposed ETA with Nexus and pre-computation optimizations, respectively. We delete them as ETA and ETA pre. ETA all means initializing all edges as candidates, which has too many candidates and will affect convergence. We observe that ETA pre has comparable and even higher object value due to our tight upper bounds, and initializing all the edges leads to slow convergence. We can observe that ETA with pre-computation is almost 400 times faster than ETA. Since transfer convergence convenience is one of the main performance indicators of a connected transit network, we evaluate the newly planned routes effect to the commuters along it, which are composed of an original stop and a destination stop in the new route. First, we measure the number of transfers are needed in the old network, and then the ratio of shortest path travel distance via the new bus network over that via the old bus network. Finally, we get the number of existing bus routes that share common stop with the newly planned routes. We plan routes for 5 boroughs of New York City, respectively. It shows that a connectivity aware route planning can help the commuters along the new route avoid up to 4.7 transfers on average in the Bronx of New York City, while a normal demand aware planning can only avoid 1.6 transfers on average. Our visualization also shows that more routes need to be built between Queens and Brooklyn, which will further connect more routes to Staten Island. For Manhattan, existing subways and bus systems are very mature, and the connectivity increase will not be obvious. And the newly planned bus routes are not necessary. This is also consistent with the fact that New York City is redesigning bus routes in the other 4 boroughs except for Manhattan. However, more routes should be planned to connect Manhattan and the Staten Islands, which highly depends on buses, while there is only one internal subway line on this island. The Bronx also need to connect north and south to form a cycle from Yankee Stadium, Hans Point Avenue, and Kingsbridge. Overall, our city bus is the first work that considers both demand and connectivity when planning bus routes, and our proposed algorithm and bonds can accelerate planning to a great extent. Most importantly, city bus can plan effective routes in 2 of the US most complicated bus transit network systems, New York City and Chicago. In the future, we hope that we can apply our algorithm in the New York City bus network redesign, and we will also try to build a benchmark of the whole world's bus networks, transit network, and people can easily access the network and compute their connectivity and further enhance their networks by building new edges, new stops, or new routes. Thanks for your watching, and I'm very happy to take questions.